Okay, the next topic we want to talk about is what's called the average rate of change. The average rate of change. So what do we mean by that? So let's take a simple example. Instead of taking a business example, I'm going to just take a simple physical example. So suppose that we have a building and we standing on the top, and we take a ball and we drop it. So we want to talk about the speed, or the speed of the ball. And what do we mean by speed? So the speed is the change in position, which we'll call d. We'll call this the distance that it's fallen. We'll call it d. Actually, usually they call it s, but d seems like a more natural symbol to use, so we'll just call it d, but usually they call it s. Okay, but the change in distance over the change in time is what we mean by the speed. So this is going to be an average rate of change. So for example, suppose that, let's say this is at t equals 0. Let's say the distance is, let's say d is the distance that it's traveled. So even though, suppose d was equal to 10 here, it wouldn't be negative 10. We'll call it positive 10, even though you might think of it as negative. But we're just talking about the distance that it's traveled, so we'll call it 10. So at t equals 0, d is also 0, let's say. And then at t equals 1, let's say it's traveled, t equals 1, let's say d is equal to 10. And let's say at t equals 2, let's say that d is equal to, let's say 40. And let's say at t equals 3 seconds, let's say d is equal to 90. Okay, so let's suppose we have that scenario. And then we want to know what is the speed between t equals 0, and t equals 1. So we would say, well, how far has it fallen in that 1 second, in that first second? So the initial, or the ending position was d equals 10. That's here. And the beginning position was d equals 0. And the change in time was, at the end was 1, and at the beginning was 0. So that is delta d over delta t, and so that is 10 over 1. So we would say the average speed in that second was 10, let's call it meters per second. Let's say we're talking about meters here. Okay, next let's find the average speed, or the speed in the second. So from t equals 1 to t equals 2. So what would that be? So that would be the position at t equals 2 is 40. Position at t equals 1 is 10. And the time interval at the end is 2, and at the beginning is 1. So we get that. So what do we get? We get 30 over 1. So the average speed in the second interval was 30 meters per second, let's say. And let's do the same thing for the last interval. So at the end of the third second, it's at 90. And at the beginning of the period, it's 40. The distance it's traveled is 90 minus 40. And again, it's 3 minus 2, or 1 second. So now it's 50 meters per second. Okay, so we have the average, this is called the average rate of change. In this case, the average rate of change is speed, but we could talk about other things. For example, in the textbook, they talk about the change in consumer price index. So that's CPI, and the change in the CPI. We could do basically the same thing for the CPI. So we'd still have time as this variable, but we could have the change in the CPI on the top, and we could do the same kind of thing. We could say how much did the CPI change, say in year 1, How much did the CPI change in year 2, the average change in year 2, what was the average change in year 3, and so on. Okay, so this gives us the average rate of change for this example. Okay, so the next thing is, suppose that we're sitting here at we're like on this floor in the building, and we're watching the ball go past us, and we want to know how fast is the ball moving as it goes past us. So let's say that when, say, what was the last one? Sorry, this one was, say, 40. So let's say this was t equals 2, and this distance was from here to here was 40. Okay, so let's say the distance was 40. So this is t equals 2. It passes right by us just exactly at that time. So we want to know how fast is it going exactly at that moment. Now we already found out that the speed that it was going between 2 and 1, we already did that calculation, that was here. So that was 40 minus 10 over 2 minus 1. We already found out that the speed was 30. But if we did the we didn't do this calculation, but suppose we did between t equals 2 and t equals 0, and we calculated that, the average speed between t equals 0 and t equals 2. So that would be what? That would be on the bottom, we have delta t, so that would be t equals 2 minus t equals 0. And on the top, we have 40 minus 0, or 40 minus 0. So that would be 40 divided by 2, which would be 20 meters per second. So in the interval between here and here, it was going 20 meters per second, but the interval between here and here, it was going 30 meters per second. So what should we choose for the speed exactly as it passes the window, passes our window? So should we say it's 20 meters per second, or should we say it's 30 meters per second? So, well, I guess we would probably say that 30 is a better approximation of it than 20 is, because then we're considering sort of a time interval, a shorter time interval closer to t equals 2 seconds. So if we use this, we get an approximation of 20 meters per second, but if we use this interval, we get an approximation of 30 meters per second. But suppose we wanted to be more accurate, then we might use t equals 1.5 and t equals 2. So then we'd have to figure out what the distance, and I didn't give any value for that. But in my head, when I was creating these values like 0, 10, 40, and 90, what I was using in my head to generate those values was this: d equals 10t squared. So you can see when t equals 0, I get d equals 0. When t equals 1, I get d equals 10. When t equals 2, I get 40. And when t equals 3, I get 90. So you can see where I was generating these values from. So if I use this for t equals, we said 1.5, we'd have to put 1.5 into here. What is that? That's 1.5 squared is, I think, 2.25. So if that's right, then d is equal to 2.25 times 10. Well, 2.25 times 10 is 22.5. So then we would do what? Then we would take delta d over delta t, and that would give us, can you read that? Yeah. Delta d over delta t would give us the distance is 40 at the end, and we're only going back as far as 1.5, so 22.5 over, and only 0.5 is the time interval in this case. So then we're going to get something different. What are we going to get? Can you read this? We're going to get, let's just erase this. Let's just make it 22. So we're going to get approximately 18 over 0.5, which is 36. Okay, so now, let's see. So what do we have so far? Our first approximation, if we did from t equals 0 to t equals 2, was 20. And then our second approximation when t equals 1 to t equals 2 was 30. And now if we go t equals, what is it? When t equals 1.5 to t equals 2, now we get about 36. Okay, so we have another approximation. Then instead of 1.5 seconds, we could use like 1.9 seconds. Okay, and we could check that. And who knows what we're going to get? You know, it's going to be a little bit of a messy calculation. But what are we actually? So what are we doing? I said I tried 0 and 2. I tried 1 and 2. I tried 1.5 and 2. I said let's try 1.9 and 2. Let's try 1.99 and 2. Let's try 1.99999 and 2. Right, what am I doing? I'm pulling this t closer and closer to 2. So I want to know what the speed is closer in a shorter and shorter time interval based on where I'm sitting, based in that window. And I'm based where I'm sitting and watching through that window. Okay, so what are we doing? What did we do when we did these calculations? What we did was we took delta d over delta t. But what was that? That was, let's say, d2 minus d1. So the beginning position was d1, and the end position was d2. Right? Yeah. And then we did delta t, which was t2 minus t1. So that's what we've been calculating each time. And I also said I was using some special formula to generate those numbers. And what was that formula? I erased it, but what was the formula? The formula was, where was it? Was, just do something here. Okay, the formula was d equals, what did we say? 10t squared. That was the formula I was using to generate these values. So let's say that, so we can say that d is some function of t. That's what I have here. D is a function of t. So let's, instead of writing d, let's write the function of t there. So we could rewrite this as, still leave the bottom the same, t2 minus t1. See that? Yeah, t2 minus t1. But instead of d2, I'll write f of t2. Because how do I get d2? I put in t2. So it's f of t2 minus f of t1. Okay, so that's what we're doing. And f is this function here. This is f of t. Okay, so that's what we're doing when we've done all those calculations. So we just put in a different t. Actually, t2 was always 2, but we chose a different t1, and that gave us a different value here. We had a fixed value here. The fixed value here was 40. This was always 40, but we did 40 minus something, 40 minus something. And we're just letting, what we did is we let t1, we started with t1 equals 0, then we let t1 equal 1, then we let t1 equal 1.5, then we suggested letting t1 equal 1.9, and we suggested letting t1 equal 1.99. And so what we're doing is we're moving t1 closer and closer to 2, right? Closer, this is getting closer and closer to 2, or we call the t2 stands for 2. So we're letting t1 get closer and closer to t2 and doing this calculation. And each time we hope to get a better approximation to the actual speed as it exactly passes our window. So we're talking about something which is called the instantaneous speed. Instantaneous speed. And, you know, that sounds like a kind of, like a, what do I want to say? sounds like it doesn't make any sense, instantaneous speed. But on the other hand, when you're driving in your car and you look at the speedometer and you say, how fast am I going? You sort of believe in this concept of instantaneous speed. So, how fast are you going exactly now? But really, speed, you can't say exactly now. You have to say, in some time interval. You're not going anywhere exactly now. So if you narrowed the interval down to a time interval of 0, you don't actually move. But we're sort of thinking about it abstractly, and what would we sort of do to figure out better and better approximations. And so to get better and better approximations to how fast we're so-called moving right now, we decided just now that what we should do is let T1 approach T2. So let's just write that down. And we've spent a lot of time, and we have the tools to write that down. So let's write it down with the tools that we have spent so much time talking about. So what tools are we talking about, or what tool are we talking about? Well, we want to calculate this thing here. So let's write that thing. F of T2 minus F of T1 over T2 minus T1. And then we just said that we want to let T1 get closer and closer to T2. So we have spent so much time talking about that, and that would be what? The limit as T2, this thing, T1, this thing, gets closer and closer to T2. In this case, T2 was 2 seconds, but so I could say it gets closer and closer to 2. That's fine. And so that's what we're looking for. Or we could say T2. If I just want to be more general, I could say T2. But in our case, we were talking about T2 equals 2. So we would say as T1 approaches 2. Okay, and then we can fill these in. So we can fill these in with this formula. So we can fill that in. So let's do that. Let's do that here. So let's fill it in. So f of T2 is, well, let's write the limit first. Limit as T1. Let's use, should I use, no, I'm going to make it general. T2. And let's fill in. F of T2 is 10 T squared T2 squared. And f of T1 is minus 10 T1 squared. See that? Hope so. And then this is T2 minus T1. Okay, and that is a limit problem. We spent, as we said, a lot of time talking about limit problems, so we might be able to calculate this limit problem. So now let's move it to the specific T2 equals 2, just to sort of simplify this just a little bit. But we have, this is a general situation. We want to know the instantaneous rate of change, or the instantaneous speed at T2. What we do is we take this limit as T1 approaches T2 of this ratio. Now, if this wasn't, if we weren't talking about a ball falling from the ground, but we were talking about the change in CPI, Consumer Price Index, then we might have a formula that gives us the CPI as a function of time. And if we had some formula, like here we have this formula, maybe it was the same formula, not very likely, but we might have some formula, then we could take, instead of this, we wouldn't have that anymore. We'd have a new formula for the CPI. We put that in here. We put it in here also. And we could get the instantaneous rate of change of the CPI, Consumer Price Index. We're not going to do that. We're just going to do it with this example of the ball. So let's try that. So let's find some space here to do this.